Have you ever come across like research and you're like, whoa, this is important stuff. But then you start reading it
Mm.
and you realize it's so dense and jargony. You just want the good stuff, the
Okay.
key takeaways without having to wade through a sea of technical terms.
Oh, absolutely. I think we've all been there, feeling like you're trying to untangle a giant knot. That's really what we aim to do here on the Deep Dive. We help you break down complex research into understandable and actionable insights. And today, we're diving into a really fascinating topic. How effective is computer-based scaffolding in problem-based learning for STEM education?
Yeah, exactly. We're looking at this really cool meta-analysis. It's called Effectiveness of Computer-Based Scaffolding in the Context of Problem-Based Learning for STEM Education, Bayesian meta-analysis. And it was done by Kim, Belland, and Walker back in 2018.
Great choice.
Now, just a quick reminder for anyone who might not be familiar, a meta-analysis basically combines the results of many different studies on a single topic. So it paints a much broader picture than any one study could on its own.
Yeah, it's like getting the big picture view instead of just focusing on a small detail.
Exactly. Our mission today is to figure out what this meta-analysis tells us about how using computers to provide support can actually help you learn STEM subjects when you're learning by doing, by solving real-world problems. And we really want to hone in on the most practical and relevant insights for you, for anyone who wants to learn new things effectively and really master them.
That's a great goal.
So let's get right to it. Does this research show that using computer-based scaffolding in this way actually makes a difference in how well people learn?
The short answer is a resounding yes. The study found that computer-based scaffolding has a pretty significant positive effect on cognitive learning outcomes in STEM problem-based learning. Overall, they calculated an effect size of G equals 0.385.
Okay, G equals 0.385. Now, I know we have some statisticians listening out there, but for the rest of us, what does that number actually mean?
Well, an effect size of 0.385 is generally considered to be a small to moderate positive effect. What that means in simple terms is that if you're learning about STEM subjects through problem-based activities and you have well-designed computer-based support, you're more likely to understand and remember the concepts compared to if you didn't have that support.
So it's not just a tiny, negligible difference.
No, not at all. It suggests a noticeable improvement in learning outcomes.
Got it. Now, you mentioned the study used a Bayesian meta-analysis approach. Why is that important?
Right, so a Bayesian approach actually has some advantages over traditional meta-analyses. It tries to correct for some of the biases that can creep into research. You see, sometimes smaller studies might find really big effects just by chance, and studies that don't find anything interesting might not get published at all. That's what we call publication bias. But the Bayesian method kind of levels the playing field. It uses prior knowledge and probability to give you a more realistic and reliable estimate of the true effect. So that positive finding we just talked about, the G equals 0.385, has actually gone through a more rigorous analysis, which makes us more confident in the result.
So it's like this finding has been double-checked and it still holds up.
Exactly.
That's reassuring. Now, I'm guessing that not all computer-based scaffolding is created equal, right? Did the study look at different types of support and whether some were more effective than others?
You are absolutely correct. They actually categorized the types of computer-based scaffolding into 4 main categories, and what they found is quite interesting.
I'm all ears. What are these different types, and which ones seem to give learners the biggest boost?
Okay, so the first one is called metacognitive scaffolding. This type involves giving learners prompts and tools that encourage them to think about their own learning process.
So, like, am I understanding this?
Exactly, like planning their approach, monitoring their progress, or reflecting on what they've learned. And this type of scaffolding actually showed the highest effect size, with a G of 0.384.
That makes sense to me. If you're actively thinking about how you're learning, it seems like the information would stick better.
Yeah, it's all about becoming more aware of your own learning process, and research shows that can have a real impact.
Interesting. So metacognitive scaffolding is the top performer. What comes next?
Okay, the second most effective type is called strategic scaffolding, and this one focuses on guiding the learner's problem-solving process. It's like giving them a framework to work with, like helping them to clearly define the problem, set goals, and choose the right strategies to solve it. It had an effect size of G equals 0.345.
So instead of just throwing them in the deep end, you're providing a roadmap to help them navigate the problem.
Exactly. It helps them break down the problem into manageable steps and approach it systematically.
Got it. What about the other 2 types of scaffolding?
The third type is conceptual scaffolding. This one involves providing learners with hints, concept maps or visualizations to help them understand the key concepts involved in the problem.
So it's more about giving them the information directly.
Yes, it's more about providing that conceptual foundation. And it might be a bit surprising, but this type actually had the lowest effect size of the three we've discussed, with a G of 0.126.
That is surprising. You'd think that giving learners the core information they need would be really helpful.
You would, wouldn't you?
Hmm.
But this suggests that maybe just having the information isn't enough. It seems like the scaffolding that really helps is the kind that guides your thinking about the problem and your approach to solving it, not just giving you the answers.
So it's more about teaching you how to fish than just handing you a fish. It's interesting. What about the last type?
The last type they looked at was motivational scaffolding, which aims to increase learner interest and confidence. But unfortunately, the study didn't have enough data to draw any solid conclusions about this type, which is a bit of a shame because keeping learners motivated is obviously really important.
Yeah, that's a piece of the puzzle we still need to explore further. So it sounds like the big takeaway here is that if you're designing or using computer-based scaffolding, the focus should be on tools that help learners reflect on their thinking and develop a systematic approach to problem solving.
I think that's a very good summary.
Now, one of the major goals of problem-based learning is to develop higher-order thinking skills. Did the meta-analysis examine how scaffolding affects those?
Yes, it did. They looked specifically at how computer-based scaffolding impacted three key higher-order thinking skills: analysis, synthesis, and evaluation. And they used Bloom's taxonomy as a framework for this analysis.
Okay, for those who haven't encountered Bloom's taxonomy before, could you give us a quick rundown of what those three skills entail?
Sure. So analysis is basically the ability to break down complex information into its individual parts and see the relationships between them, like taking apart a machine to understand how all the gears and cogs work together. Synthesis, on the other hand, is about putting things together, combining different ideas or elements to create something new, like taking those individual parts and building a whole new machine.
Got it. And evaluation.
Evaluation is about making judgments, deciding what's good, what's bad, what's effective, what's not. It's like looking at that new machine you built and assessing how well it works, or comparing it to other machines to see if it's better or worse.
Perfect. Thanks for the explanation. So, where did computer-based scaffolding seem to have the most impact in terms of these higher-order thinking skills?
The biggest effect was seen in analysis. They found an effect size of G equals 0.537 for that skill.
So it's really good at helping learners take things apart and understand the individual components.
Precisely. It seems like computer-based scaffolding can be a powerful tool for helping learners dissect information and understand how the different pieces fit together.
That makes sense. If you can break a problem down into smaller chunks, it often becomes much easier to tackle. What about synthesis and evaluation?
Well, both synthesis and evaluation showed much smaller effect sizes. For synthesis, it was G equals 0.156, and for evaluation, it was G equals 0.147.
So it seems like computer-based scaffolding might be less effective at helping learners put things back together or judge the value of information or solutions.
Yeah, that's the indication we get from this research. It's good at helping you analyze and understand the building blocks, but it might not be as helpful in supporting that leap to creative synthesis or critical judgment.
That's a really interesting distinction. It's almost like you need a different set of tools for those more creative and evaluative processes.
Exactly. And this highlights an area where we could potentially improve the design of computer-based scaffolding. How can we create tools that better support those more generative and evaluative aspects of higher order thinking? That's a key question for future research.
Absolutely. Now, something we always emphasize in education is the importance of tailoring support to individual needs. Did the study look at whether the effectiveness of scaffolding changes based on how it's customized?
Yes, they did. And this is where some of the most exciting findings come in. They looked at what they called scaffolding customization, which basically means adjusting the type or amount of support you provide to match what each learner needs. And what they found is that customization really matters. A lot.
I'm intrigued. Tell me more about the different ways of customizing they investigated and which ones seem to work best.
So they examined a few different approaches. First, there's the approach of dynamically adjusting support, by fading it out as the learner progresses and adding it back in when they need more help.
So it's not a one-size-fits-all approach. It's more about providing support as needed.
Exactly. It's about being responsive to the learner's progress.
Yeah.
And this approach actually had the largest effect size of all, with a G of 0.590.
Wow, that's a pretty big difference. What about just adding more support or just fading it out?
They looked at those approaches as well. And while both adding support, G equals 0.443,
Right.
and fading it out, G equals 0.429, showed positive effects, they weren't as impactful as the dynamic fading and adding approach.
So it seems like that responsive back and forth approach is key.
Yeah, it's like finding the right balance between challenge and support. Not too much, not too little, but just the right amount at the right time.
Makes sense. And what about providing the same level of scaffolding to everyone, regardless of their needs?
Well, that was the least effective approach, with a G of only 0.162.
So customization is really non-negotiable if you want to maximize the benefits of scaffolding.
It really seems that way.
Okay, so we know that dynamically adjusting the scaffolding is important, but how do you actually put that into practice? Did the study look at different methods for customizing scaffolding?
They did. They looked at a few different methods, and the most effective method they found was called self-selection. This means the learner has the ability to choose when they need support and request it.
So it's all about giving the learner control over their learning experience.
Exactly. It puts the learner in the driver's seat. And this method had an effect size of G equals 0.519.
That's pretty impressive. So learners knowing their own needs and seeking help when they need it seems to be a winning strategy.
It really does. What's interesting is that it was even more effective than having the system automatically adjust the support based on the learner's performance.
Oh, really? I would have thought that a smart system that can tailor the scaffolding automatically would be the most effective.
It's a reasonable assumption, right?
Yeah.
But it seems like having that sense of agency, that control over when you get help, is really important for learners.
That's fascinating. It speaks to the importance of learner motivation and engagement. What other methods did they look at?
They also looked at customizing scaffolding based on a fixed time interval, which means adjusting the support at predetermined points. And that had a moderate effect size of G equals 0.376. They also included studies where the method of customization wasn't clearly defined. But as you might expect, those studies show the smallest effect, with a G of only 0.122.
Right, so having a clear and deliberate method for customizing the scaffolding is crucial, whether it's learner-controlled, performance-based, or time-based.
Absolutely. The key takeaway is that customization is most effective when it's done in a systematic and intentional way.
Okay, so we've talked about the different types of scaffolding and the importance of customizing it. But what about the specific strategies or tools that are used? Did the study look at the effectiveness of different scaffolding strategies?
They did, and there are a couple of findings that I think you'll find particularly interesting.
Okay, lay it on me. What strategies did they examine, and what did they learn about their effectiveness?
One strategy that emerged as highly effective was expert modeling. This is where you show learners how an expert would approach and solve the problem. And this strategy had an effect size of G equals 0.523.
So it's like giving them a masterclass in problem solving.
Exactly. Seeing an expert in action can be really powerful for learners. It helps them understand the thinking process and the strategies that are involved.
Makes sense. What other strategies were effective?
Providing feedback was also found to be very effective, with an effect size of G equals 0.474.
So giving learners specific information about their performance helps them improve.
Absolutely. It helps them identify their strengths and weaknesses and make adjustments to their approach. Now, here's one that might surprise you. Using multiple scaffolding strategies together actually only had a moderate effect size of G equals 0.340.
Really? You'd think that more support would always be better.
You would, wouldn't you? But this finding suggests that maybe it's not just about throwing a bunch of scaffolding strategies at learners. It might be more about choosing the right strategies and using them in a way that's well integrated and tailored to the specific learning task.
So it's not just about quantity, it's about quality and strategic use of scaffolding.
Exactly. Now, here's another finding that might raise some eyebrows. Providing learners with question prompts to guide their thinking had the lowest effect size of all the strategies they examined, with a G of only 0.078.
Wow, that is surprising. I mean, question prompts are such a common teaching technique. Why do you think they might be less effective than, say, expert modeling or feedback?
That's a great question. And to be honest, the answer isn't entirely clear. It could be that the effectiveness of question prompts depends heavily on the types of questions being asked and how well they're designed. Maybe the questions used in some of the studies they analyzed weren't challenging enough or specific enough to really guide learner thinking. Or maybe it's about asking the right kind of questions at the right time. Questions that require learners to explain their reasoning or reflect on their learning process might be more effective than just asking them to recall facts.
So it's not just about asking any old question, it's about being really intentional with the questions you ask.
Exactly. And it highlights an area where more research is definitely needed. We need to understand better how to design and use question prompts in a way that maximizes their effectiveness as scaffolding tools.
Absolutely. Now, STEM is a pretty broad umbrella term. Did the study find any differences in the effectiveness of computer-based scaffolding across different STEM disciplines?
Yes, they did. They looked at science, technology, engineering, mathematics, and integrated STEM curricula, and they found some pretty big differences.
Okay, so which disciplines showed the biggest benefits from scaffolding?
Engineering actually had the highest effect size, with a G of literal 0.528.
So computer-based scaffolding seems to be particularly helpful for learning engineering concepts.
It seems that way. And mathematics wasn't far behind, with an effect size of G equals 0.425. And for technology, they found an effect size of G equals 0.379.
So those three seem to cluster together in terms of seeing positive effects.
Yeah, they do. And science was kind of the outlier here. It had a much lower effect size with a G of only 0.146. And surprisingly, integrated STEM education also had a relatively low effect size, with a G of 0.201.
That's unexpected. You'd think that integrated STEM, which often involves complex real-world problems, would really benefit from this kind of support.
You would think so, right? But maybe the types of scaffolding being used in those contexts aren't quite as effective. Or maybe it has something to do with how problem-based learning is being implemented in those disciplines. It's definitely an area that warrants further investigation.
It seems like the specific context of each STEM discipline really matters. The types of problems, the learning goals, even the way the curriculum is structured might all influence how effective computer-based scaffolding can be.
I completely agree. It's not a one-size-fits-all solution. It needs to be tailored to the specific needs and characteristics of each discipline.
All right, let's zoom out a bit and think about what we've learned today. What are the key takeaways from this deep dive into computer-based scaffolding in STEM problem-based learning?
First and foremost, the research clearly shows that computer-based scaffolding can be a valuable tool to support learning in these contexts. But, and this is a big but, the way you design and implement that scaffolding is absolutely crucial. It's not just about throwing technology at a problem and hoping for the best.
So it's not just about having computers in the classroom, it's about using them strategically and thoughtfully.
Exactly. It's about choosing the right types of scaffolding and customizing them to the needs of individual learners. And the research suggests that metacognitive and strategic scaffolding are particularly effective approaches, those that guide learners' thinking and problem-solving processes, rather than just giving them the information directly.
And dynamic customization is key. Being responsive to learners' needs, whether through self-selection or performance-based adjustments, seems to be more effective than just providing a fixed level of support.
Definitely. And in terms of specific strategies, things like expert modeling and providing feedback have strong evidence behind them. While question prompts, surprisingly, might not be as effective as we often assume. But of course, all of this can vary depending on the specific STEM discipline you're talking about.
So there's no magic bullet, but there are some evidence-based principles we can use to design really effective computer-based scaffolding for STEM problem-based learning.
Exactly. It's all about being thoughtful and intentional in our design and implementation.
I think this leads to a really interesting question for our listeners to ponder. How do these findings about computer-based scaffolding connect to your experiences of learning, whether it's in a formal educational setting or just in your everyday life when you're trying to learn something new or solve a complex problem? What kind of scaffolding do you find most helpful? Is it having a mentor who can guide you? Is it finding a well-written book or online resource? Or maybe it's about developing your own self-monitoring strategies.
That's such a great question. It really encourages us to think about our own learning preferences and what helps us succeed.
And if this deep dive has sparked your interest in learning more about this topic, I highly recommend checking out the original meta-analysis by Kim, Belland, and Walker. And of course, there's a wealth of other research out there on computer-based scaffolding and problem-based learning. Thanks for joining us on this deep dive. We'll see you next time.
Thanks for having me.